We know that many companies have tried and failed to measure blood glucose non-invasively. Now, why is that? We know that we can measure heart rate. We know how to measure blood oxygen non-invasively. But for some reason, we seem to struggle with blood glucose. Why is that? And what is it that makes blood glucose measurement so hard? Well, that's what we're going to explore and try to understand in this video. Hi, welcome back to the channel. Hope everybody is happy and healthy and staying well and getting out there and exercising. So accurately measuring blood glucose requires a great deal of sensitivity and specificity, as well as a minimum of interference from other extraneous factors. And so we call this sort of the signal-to-noise ratio. And in this video, we're going to explore the biology, the physics, the mechanics of measuring blood glucose non-invasively to better understand the challenges we need to overcome. And we're going to start with glucose itself. So the first thing to know about it is that we don't actually have a lot of it in our bodies. With a normal blood glucose concentration of between 70 and 100 milligram per deciliter, and the average person having about 5 liters of blood, that translates into about 5 grams or a teaspoon of glucose in our bloodstream. That's very little. And given the range of people's body sizes, we're really talking about something from 3 to 7 grams of glucose for the average person. So the first challenge we have, obviously, is that we need methods that are very sensitive and sensitive enough to obviously detect minute quantities of glucose circulating in our blood. There is additional glucose in our body that is free, including in the interstitial fluid, the ISF, that we're going to talk about in a bit. We have 3-4 times more ISF than we have blood, but strictly speaking, blood glucose is different from glucose in the ISF, and that's an important distinction that we're going to talk about later in this video as well. Next, glucose is not very descript and completely colorless. Just mix some sugar in a glass of water. Can you see the sugar? Can you visually tell the difference between a glass of water with sugar and without? No, of course not. It just dissolves in the water and becomes invisible to the naked eye. Glucose is also present in many cells and tissues and is attached to many proteins. And there are many molecules that are similar to glucose or glucose derivatives and appear very similar in the methods that we have available to us and that we use, which, of course, further complicates things in terms of detecting this. All this presents a second challenge. We need methods that are specific and selective enough to detect glucose and not be fooled by other chemicals that are similar to or derivatives of glucose. So given all of this, how do we actually measure glucose? Well, it might be useful to start by looking at how we measure glucose when we actually get blood through finger pricks. And those of you familiar with it will know that there are 2 different methods for that. It's the enzymatic method and the hexokinase method. And the interesting thing about them is that neither of them measures glucose directly. Rather, they measure glucose indirectly. In the enzymatic method, glucose is converted to hydrogen peroxide, which is then electronically oxidized, I apologize for the gobbledygook, to generate an electric current. And it's the electric current that we actually measure. So those of you who've used sort of devices that you stick the glucose strip into, what the device does is that it actually measures the electric current, which is proportionate to the concentration of glucose in the sample. Let's remember the enzymatic method because it actually has some applicability to non-invasive glucose monitoring that we're going to talk about in a little while. Now, the hexokinase method consists of a number of chemical reactions, ultimately producing something called NADH, which can be measured using light waves at the 340 nanometer wavelength, which is the frequency of light it absorbs. And because it requires multiple chemical reactions, it's not applicable or useful for non-invasive glucose monitoring. So we can completely and totally forget about it, at least for the purposes of this video. Now, what is worth remembering is that both of these methods, as we said, are indirect. They don't measure glucose directly, and so it obviously raises an interesting question. What does it tell us about our ability to measure glucose directly when we're trying to do it non-invasively. Now, if you find this video useful or interesting or entertaining or anything else, don't be shy about clicking the like button and subscribing. It doesn't cost you anything and it's much appreciated. Now, if we're going to measure blood glucose non-invasively, obviously we need to talk about the skin. To get to the capillaries and blood in our bodies, we obviously need to get past the skin, the liquids, and other cells underneath the skin, all of which potentially hinders, weakens, or distorts any signals, whether it's light or radio frequency or anything else that we may want to be sending into our body to try to detect blood and blood glucose. And it turns out that skin is actually quite complex. It consists of three main layers: the epidermis, the dermis, the hypodermis, as in this picture. The outer layer, the epidermis, consists in turn of 5 layers and has the least ISF. The dermis consists of 2 layers and is comprised of 70% water by mass at least, a big chunk of which is the ISF. Now, using light as an example, as light penetrates skin, there are 3 things that happen. It's absorbed, it's scattered, and it's reflected by various elements that it travels through, whether it's collagen or lipids, including fats or water and other constituents. And different frequencies of light are obviously absorbed and scattered and reflected to different degrees, which is an important consideration. The absorption of light in our skin is also impacted by other factors, whether it's sunlight, temperature, pressure, as well as the amount of melanin in a person's skin, the thickness of the skin, hydration levels, activity. So there are lots of things that can potentially impact the accuracy and reliability of the measurements that we do that has to go through the skin. And to complicate matters further, the concentration of glucose in the blood and the ISF itself will also impact the degree of scattering of light and other frequencies in tissue. And so we need to consider 2 different issues. First, do we have the methods that can both reach deep enough under the skin to reach our arteries and our blood, and are specific enough to detect glucose and not get confused by other chemicals? And if the answer to the question is no, where are we going to find blood glucose and how are we going to measure it? Are we going to measure it in the ISF, or are we going to use sweat, saliva, skin, surface? And if so, how reflective is that of, and representative is that of actual blood glucose? It gets a little bit complicated, but we're going to sort it out. So to address the first question, we're going to use light waves as an example because, well, first of all, many companies looking to develop non-invasive glucose monitoring are using some spectrum of infrared light. And because the challenges we encounter with light are illustrative of the challenges we're going to encounter with other approaches that we're going to use. So if we look at using light waves for measuring blood glucose, the fundamental challenge is that we know that some waves lengths that might be good enough for detecting glucose in the blood do not penetrate deep enough, and others that penetrate deep enough are not specific enough to clearly detect glucose. So the question is there a happy medium? Well, let's see. Now, one complicating factor here is that water and glucose have the same propensities to absorb specific wavelengths of lights. So that's something we need to deal with, especially since there is more water than there is glucose in the body. That can sort of become an issue. And there are many other compounds, as we said, that are similar to glucose, at least in their signatures for our detection methods. So we're going to look at different wavelengths of lights because they behave differently. And so we're going to start with infrared, with near-infrared light. And the good news here is that near-infrared light are not absorbed by water, which means that the vast majority, some 90-95% of it, can pass deep into the skin and into the capillaries. The downside here is that it has a high degree of scattering in tissue and does not differentiate well between glucose and other proteins and acids that we have that have similar characteristics as glucose. In other words, near-infrared light is not specific enough for our purpose. By the way, and because it makes for good comparisons, there are reasons that we can measure blood oxygen or pulse ox using light, and that is that oxidized and non-oxidized blood shows different absorption of red light and infrared light, specifically the 616 nanometer and the 940 nanometer wavelengths, or what we're using for blood oxygen. They can reach deep enough so they can reach into the capillaries and can actually measure it directly in blood, and are also specific enough. Now, this is what real pulse oximeters do, the ones that you buy at the pharmacy. They shine light from the top of your finger and catch it with a sensor at the bottom. That is not how smartwatches work, which is why pulse ox on smartwatches is less accurate and less reliable. Now, getting back to glucose measure. Next, we need to talk about mid-infrared spectrum with a different set of wavelengths. The good news, it has less scattering due to a longer wavelength, and many molecules have very unique spectra of absorption in this range, which makes it a good wavelengths for detecting molecules. Unfortunately, it is highly absorbed by water. It has very limited penetration underneath the skin, like a few micrometers, which means that it doesn't reach anywhere near our blood vessels. So obviously that doesn't help us either. And other light frequencies aren't much more useful. Far infrared light is also highly absorbed by water. Microwave and millimeter radiation goes deeper into the tissue to reach glucose, but has poor selectivity. So that's the trade-off we're sort of facing, especially when it comes to light, but also other frequency approaches. It's reach versus selectivity. Can we actually get at blood? And if we can we do it well enough? And if we can't, then what are we going to do instead? I actually believe that is why Rockley Photonics, if you remember them from my 23-24 video, when they were thinking about developing their chip, they were going to develop a chip with multiple light frequencies, different infrared spectra, and I think what they were looking to do is to combine the information from all of these to try to make sense of it. So given what we just learned, doing non-invasive glucose monitoring by monitoring the blood directly doesn't necessarily look that great, and that raises the question that maybe we have to look at some substitutes, whether it's the ISF or saliva or tears or sweat or something else that can give us a reliable value but isn't blood, and it's easier to access. And that presents a set of challenges in its own right, of course. Because if we go to a different medium, whether it's the ISF or saliva or something else, isn't going to have the same concentration of glucose as glucose has in blood, and isn't going to be consistent or isn't going to fluctuate. We know that the changes in blood glucose take some time to translate into changes in glucose in the ISF, for instance. People have estimated that it might take 6 to 12 minutes. Others have estimated about 15 minutes, and the reality is that the time lag here, the physiological time lag as it's called, may actually not be constant, which is, of course, a cause of concern. It might be changing depending on other circumstances. And the third issue we have with measuring blood glucose, or a substitute for blood glucose in some other media, is that there might be other external factors that mediate it as well. It could be temperature, level of hydration, hormones, medicines we take, food intake, exercise, and potentially other things as well. So there are definitely things to consider if we're going to measure blood glucose in a substitute liquid in our body. You know, one interesting thing to consider that has been raised with regards to the ISF, that if we're going to use the ISF, are we going to measure glucose in it underneath the skin, or we're going to try to pull it up to the level of the skin surface, and measure it there? And in fact, if you remember the 23-24 video, there is in fact a company, a French company, that is looking on doing just that. They're looking to pull the ISF through the skin and into an enzymatic sensor. And the good thing about that, of course, is that we've talked about enzymatic blood glucose detection. We know that that works. So the question is only, can they pull up the ISF through the skin and do it reliably enough. And another potential option is, of course, to try to measure some substitute measure of blood glucose on our skin directly. That's also something that's been suggested because there are distinct biological changes that occur as a result of blood glucose changes. So where does that leave us? Well, it's a little bit complicated, but I think we knew that at the outset of this video, which is why we don't have non-invasive blood glucose monitoring yet, although people are working on it. Clearly, our ability to non-invasively measure blood glucose directly in blood is not looking that great. We're sort of back to the trade-off of specificity versus depth, and light waves that can reach deep enough or not specific enough, and those that are specific enough don't reach deeply enough to actually be able to measure in blood directly. Maybe those two methods can be combined, and I think some people are trying to do that, and we'll see how well that works for them. So the alternative is there clearly to try to measure blood glucose somewhere else, whether it's in sweat or saliva or the ISF, or maybe on the skin, as we've talked. Our best bet seems to be to measure blood glucose in the ISF using mid-infrared light or other waves on similar frequencies, whether it's radio or something of that kind. We know that there are challenges associated with them. We talked about them in terms of how well the glucose concentration in the ISF reflects blood glucose concentration at any particular point in time, and how consistent and predictable and reliable the time lag is. So there are definitely challenges to be addressed. That said, I'm optimistic. The challenges we've discussed are not new. On the contrary, I think they're very well known and very well documented. There are many interesting efforts underway to address them, as I think you know from my other 23-24 video. I will leave a link in the description to those of you who haven't seen it who might be interested. And so I still remain optimistic that we can overcome these challenges. So hopefully you found this video interesting. Hopefully going forward it will help you understand a little bit better the challenges that companies that are working on non-invasive blood glucose monitoring are facing and that they are working to solve. So with that, if you have any questions or thoughts, please let us know in the comments below. Thank you for watching, and be well. We'll talk to you soon. Take good care. Bye-bye.